Can you hear me? Yeah, that's a lot different, isn't it? All right, so apologies for that. We're just going over the agenda in case you didn't hear me speaking, and today we'll be talking a little bit about WebWorks HTML5, what you can get with WebWorks in your HTML5 application, Canvas 2D, WebGL, sort of go over the basics, and we'll look at two sample projects that are available on GitHub today, TunnelTIlt and Peaks and Valleys. So let's take a quick look at WebWorks before diving in further. What can you get? Why would you bring your application natively to the platform when you already have it hosted on the web? Well, when you package your app with WebWorks and distribute it, you can monetize. You get access to App World. You get access to the 80 million subscribers that we have. You can hide your source code. Everyone knows on the web, any browser that can hold its weight, you right-click, view source, and you get to see how everything is done. When you package your application and distribute it to a device, there's no way anymore for somebody to take a look at that application and see what it's built of. You get access to a lot of APIs, so including device motion, file access, GPS. A lot of these you get inherently with HTML5 now, but something like payment services integrating virtual goods right into your application that people can purchase, you get that with the WebWorks APIs, and you can integrate that into your application directly. And you also get extensions. On the Playbook, these extensions were built with ActionScript. On BlackBerry 10, these extensions will be native, or are native C and C++ extensions. We have templates and tutorials online, so if there's any native functionality that you want from the device that isn't offered through HTML5, you can build these extensions to do that for you. And there's a multitude of other things out there. Things like social integrations with BlackBerry Messenger, if you want to have that integrated so that people can share your application socially, communicate with their friends, all of that's open up to you by bringing your application into a packaged WebWorks app. But let's focus on 2D for a moment. Canvas 2D, hands up if you're familiar with the canvas element in HTML5. All right, so a couple of hands. What you get here is basically a canvas that you can draw to, and the sky's the limit. There's a difference if you've done Flash development, if you've used some other technologies out there is no scene graph. That means there's no sort of structure of objects where you have this element is a child of this parent, and that sort of relationship between objects. On the canvas, you draw something, and if you haven't stored the information about that something somewhere else, then it's gone. Each frame, you have to redraw it, and if you don't remember, well, basically, it's not going to be there anymore. So you have to do all this yourself. The nice part is, though, that it's pretty easy to use the canvas. You can see there we're setting up a canvas, so a rendering surface with a specific width and height, and if it's not supported, well, we let the user know. The canvas, we have to get that element, and from that we get our 2D context. And this context is where you will do the majority, what you will use for the majority of your functionality. Drawing lines, circles, bitmaps, images, all of this rendering is what you get through that context object. There's a lot you can do. You can see just a few examples up here on the screen of the various things you can do. So gradients, animations, scaling. Basically, anything that you desire to do with this canvas, the functionality is probably there. If you want to get crazy, then there are some other options available to you, which we'll talk about in a moment. But basically, all of this, multiple rendering services, multiple canvases, you can use that to build up your 2D application and provide the user with that experience that lets your application stand out from something else. So here's a really quick basic example of drawing a path. You can see first, we're starting in the top left corner, we're beginning the path, and we say that we're moving to the position 3, 0. So these are x and y coordinates. X equals 3, y equals 0. That's our starting point. Next, we're drawing a straight line to 10, 0. And now we have these other options available to us, not just straight lines. Now we're drawing a quadratic curve. And we keep on drawing these lines And I'm not sure if you can see the outline around the outside, but we've sort of traced that shape there all the way around. And in this case, that shape is a part of a bigger shape. And we have a code sample here that shows how you can take what you just drew, reposition it, and draw that same object over and over. So it's open to you to not only draw objects, draw shapes, but do it efficiently. On the playbook, we have a hardware-accelerated canvas. Basically, this means that the drawing, all that processing is done on the GPU. On BlackBerry, on the Playbook 2.1 OS, so soon to be released, an update for the general public, we have updated graphics drivers to make that improvement in performance even better. So applications previously that were running at maybe 10, 20 frames per second are now running at 50, 60 frames per second. With the hardware acceleration on the GPU, we saw a huge increase in performance, and now we're seeing, again, another huge increase in performance. And with BlackBerry 10, it's even better. Comparing 2D and 3D applications on the latest version of versus BlackBerry 10, there are huge performance improvements still. So if you ever hear people tell you, well, you just don't get performance with WebGL, you don't get performance in the browser, not the case. There used to be a large divide, but that divide is rapidly shrinking.
So BB10 also has hardware acceleration?
Sorry?
BB10 also has hardware acceleration?
Correct. The BlackBerry 10 browser is essentially an improved upon browser that we had in the playbook. It is much different in many cases, but it also has hardware acceleration, correct. Question?
What was that on the 2.1 playbook? Okay, sorry.
No problem. Yep. So that's where we had some updated graphics drivers that resulted in performance on 2.1. A really quick example that I want to show you, Cocos 2D HTML5 is a fairly new framework. The sprite art that I'm using and the tile art that I'm using is taken from other artists, so I just want to give them credit there. And I've also created a controls overlay.js. Now this is open on GitHub right now. It'll be promoted to the BlackBerry repository soon. And this is a way to provide you with control mechanisms, so joysticks and buttons within Cocos 2D HTML5 to make that control easier for you. So if we could please switch to the device. You can see our hero here standing around, not doing much, not being very heroic, in a very colorful world. And you can see in the bottom right corner, we have a few controls that we're not actually using right now. Regardless of where I click on the right-hand side of the screen, I have a joystick that pops up and adapts to wherever my finger is. Now, I like this part because who's ever tried to play a game and you have to really get that control in there? You can't always hit it. So this one here is meant to allow you to adapt to what the user is doing. On the right-hand side, you can make them turn around, hit a few buttons, a few actions, and this is all the Cocos framework here, animating, and it wouldn't be a proper hero if you couldn't moonwalk a little bit. All right, could we please switch back? So now we want to talk a little about WebGL and 3D. This is sort of the main focus of this talk. And for that, to kick it off, I'll hand it over to Jonathan.
All right, thank you very much. All right, so Eric's given us a nice overview of the Canvas 2D API. And now I'm going to jump into WebGL, which is a different HTML5 rendering technology. Before I start, I actually wanted to mention that we are the first tablet to ship with a functional WebGL implementation, which we were really excited about. Yeah.
Cocos 2D is a framework for the canvas. So just 2D animations and rendering like that.
OK, so there's a variety of different ways to think of WebGL. I'm just going to go through a quick what is WebGL from a variety of different perspectives. So the first perspective is it's an open standard created by the Kronos group for drawing 3D graphics in the web. another approach that you can another way you can kind of look at WebGL is it brings 3D drawing to the HTML5 canvas tag. So before you would create a canvas and you could get a 2D graphics context. Now you can create a canvas and you can get a WebGL graphics context that you can do 3D drawing with. Additionally, the way I kind of think of it as a browser implementer of WebGL is that it's simply a set of JavaScript bindings or wrappers on top of your OpenGLES 2.0 commands. Another way you can kind of look at WebGL is more of the pipeline. So it's very similar to the OpenGLES 2.0 pipeline that you see here. So what's basically going on here is in the first stage, you're going to be buffering up some geometry. You're then going to be using a vertex shader to transform your vertex data from one location to another location. Then you're going to have some connectivity information that's associated with the vertices that you're using. And you combine that information into a set of primitives. Those primitives will be essentially projected onto your screen and will be broken up into a set of pixels or fragments. And each of those fragments, we'll run a different program called the fragment shader on it, which is responsible for the output color. As you can see in that last diagram, we're essentially interpolating the colors from our vertices to get that result. There's also another kind of perspective that you can take when thinking about WebGL, and that's that it's a client-server interface. So when you're making WebGL calls, they're actually going to go to your GPU, and they'll be buffered up. And the GPU can handle them at its own discretion. So that way you kind of get this parallelism and this speed improvement. In fact, the GPU is even broken up into a variety of different pipelines that run in parallel. So you just get this really great performance benefit. OK, so now what we're going to do is we're going to walk through a very simple example. We're going to talk about how can I draw a triangle with WebGL. So we're going to break it up into 5 components: how to create a canvas, set up a render loop, buffer up our geometry, set up our shaders, and then finally render the content. OK, so just out of curiosity, quick show of hands. How many people have used OpenGLES 2.0? OK, very small number. OK, so some of you guys might know that to set up a surface was actually a lot of work. You had to do all this stuff with EGL. And the great thing about WebGL is that a lot of that work is kind of thrown out. All you have to do is you create a canvas element with a specified width and height, and then you get the context from that canvas. And then you're ready to go. You can basically use that to run any functions that relate to WebGL. So the next thing that we are going to talk about is, so how do we set up the render loop? So there's actually 3 different ways we can set up this render loop. We can use setTimeout, which will call a specified function after a given amount of time. In this case, I'm using 1,000 over 60, which represents an attempt at maintaining a 60 frames per second frame rate. Or you can use setInterval, which will actually continually call your function after the elapsed time. So setTimeout, you'd have to keep calling setTimeout in order to get that render loop to function. And then finally, there's window.request animation frame. This is actually the recommended approach for setting up a render loop. And the reason why is, first you pass it a render function, and the browser is in charge of rendering you as it can. And it will never exceed the refresh rate of your display. But additionally, you pass in your canvas. And what's really cool about this is if your canvas goes off screen or is in an off-screen tab, then it won't bother rendering you, which is one of the benefits of using window.request animation frame. OK, so the next step is buffering up your geometry. So how do we go through that process? So essentially, the first thing we do is we create a buffer on our GPU for this data. In this case, we're passing position information. And we call buffer data to actually pass this data to the GPU. We're going to do the same thing. We're going to create a color buffer for our color information. We're also going to pass this data to the GPU to deal with. Now, you can actually, in this case, we've created 2 separate buffers for our position information and our color information. But you don't actually have to do this. You can actually specify a single buffer and basically share that data. Use one buffer and share it between your 2 different types of data. So you can either have all your color data followed by all your position data, or what's more commonly done is you can interleave your data. So you can have position, color, position, color, position, color, position, color. In our example, we're creating 2 buffers, though. But just keep in mind that there might be more efficient ways of doing this. OK, so at the heart of WebGL programs are shaders. So this diagram here kind of shows the inputs and outputs to these different programs. So a vertex shader takes attribute and uniform information as inputs, and a fragment shader just takes uniforms as inputs. Attributes you can think of as per vertex values. This is stuff like your positions, your colors, your texture coordinates, your UVs, etc. Your uniforms can be thought of as constant data for a set of primitives that you're drawing. So this might be something like your matrix that's going to transform your vertices from one location to another. And another type of uniform that a fragment shader might take might be a sampler, which is basically a texture map that you might want to be able to pass into your fragment shader. As outputs, your vertex shader outputs obviously your position, because you might have transformed the vertex from one location to another. And it also outputs varying values. Varyings are probably the most complicated one to understand of all the types. Varying value basically is an interpolated result. So for example, with the color image I showed earlier, over here, in the diagram on the bottom right, you can basically see that I'm outputting interpolated values. Those interpolated values are through varyings. So you'll get an interpolated result based upon your attribute information. Oops, sorry. Just going back. OK, so, and finally, your fragment shader is also going to output a color for every pixel. So now we're just going to look at some sample vertex and fragment shaders that take care of this work for us. So as I mentioned, the attributes are per vertex values. So we have a per vertex color and a per vertex position. And the uniforms are constant for a set of primitives that you're drawing. In this case, that transformation matrix is going to transform your vertices from one location to another. You can see that it looks kind of like a C-like program because we have this like main method. So it should look fairly familiar to people. And essentially, we're going to output our position as being our transformation matrix times our position. And we're going to pass this varying value, which is essentially interpolating your attributes between. Yeah, sorry. You have a question? LearningWebGL.com is a great source for learning more.
Generally, like this Web4 and all these things, they are not explained in detail.
They are. Check out LearningWebGL.com. It's actually really good. It's an excellent source. Anyways, as I was saying, so you can then our fragment shader is actually outputting the interpolated color result. And there's one other thing that I should mention, which is you see this precision high P float. That's actually mandatory, that you must specify the precision of floating point data types inside of your fragment shader. So for most of you, it'll just be remember to copy this line and paste it in here. But I'll talk a little bit later on about precision qualifiers and why they're relevant to think about for mobile. The next thing you have to do is you have to compile and link your shader programs. And now we have this other question, which is we've got this shader program that exists, and we've buffered up our position and color information. And so how do we actually pass the data into our shader program? So we have to pass our attribute data and our uniform data into our shaders. So that's where these locations come into play. So we create an attribute location variable and a uniform location variable to represent the pipe that we're going to be passing our attribute data and our uniform data down. So then when it comes to actually rendering the scene, we start off by clearing our color buffer and our depth buffer. We enable the shader that we're going to use. And then this is where we're passing our uniform data down. So we're using that transformation matrix location to pass our uniform data down. And we're going to be passing our attribute data down in just a second on the next slide, as well as drawing our primitives. OK, so that's what this code does right here. So now we're enabling the attribute locations that we care about, namely our position and color information. We're binding to that buffer for our position information. And I'd mentioned before that you can specify your data in a variety of different ways. You can interleave your data. You can have all your position data followed by a color data inside of a buffer. Or in our case, we're creating two separate buffers. But this vertex attribute pointer call is where you actually specify how your data is organized. And that enables the GPU to actually draw your data. And the actual drawing of our primitives is done by this geoDrawArrays call. In this case, we're dealing with triangles. But there's a variety of different primitive types that you can render. So you can render points, you can render lines, you can render triangles. But frequently, you want to use the most efficient method possible. So for example, if you're trying to draw two neighboring triangles, And with triangles, you'd require 6 vertices of information. But with triangle strips, you'd only require 4 vertices of information. So it's useful to minimize the size of your buffers. OK, so now we're going to move on to talk about WebGL frameworks. I'm just going to hand this back to Eric.
So I'm not sure how many people noticed, but at the beginning of that last 5-step process, we called it 5 easy steps to render with WebGL. And the fact is that it can get very complicated. And without proper documentation, without proper tutorials, it can be very tricky. Like Jonathan mentioned, Learning WebGL is a very good website to go to for more information on pure WebGL. They have a lot of documentation up there now. I'm not sure the last time you were there, but basically that's what I used myself to sort of get started in that arena. And I do want to talk a little bit about WebGL frameworks now. So this is taking those quotes off the easy word and really simplifying the process. So there are a couple out there that people might want to look at if you've already developed games using other frameworks, so 3D games. If you've used Unity or if you've used Maya, there are frameworks out there where you can import those resources into your WebGL application and leverage those directly. Cubic VR is another one that's out there. It's a full-fledged WebGL framework, so you get objects, you get easier access to that context so that you can render with minimal lines of code. The one that I want to focus on, one that's picking up a lot of steam, is called 3JS. And there's actually another project underway called tQuery, which is sort of taking 3JS and simplifying it even more. It's looking at it has nothing to do with actually implementing jQuery itself, but it's taking the same sort of design characteristics in simplification, creating objects, and then simply using those. And that's built off of 3JS. So if you are going to use WebGL or any sort of framework, I highly recommend starting at the most basic layer, being pure WebGL, and then working your way upwards towards these frameworks. That way you have an understanding of what's going on under the hood. 3JS is a framework created by Ricardo Cabello, and it is one of the more popular ones in use right now. Large community involvement. It still is getting a lot of updates, and it provides you all that stuff that Jonathan mentioned in a much simpler container. So let's take another quick look at, quick question?
Sometimes, like, I went to the 3.js site, so many, in many areas, documentation was not there. Like, for example, they just mentioned the function and nothing was there in terms of explanation or what the arguments were.
Okay. And so the question was that on the 3JS website, some of the documentation sometimes skips over a few things. There is also a website called learning3js.com, and they have a nice set of tutorials there. I would recommend starting there instead of jumping straight to the framework. That will sort of guide you through. Otherwise, because 3JS is an open source project up on GitHub, you can always get in touch with the developers there, ask questions, submit issues, and they're very responsive in getting back. So we'll take a quick look at those easy steps to render pure WebGL versus 3JS. Now this is a fairly simplified example, but it'll sort of give you an idea of what's going on. So pure WebGL, we had that canvas element that we need to draw to. 3JS, basically, we're including the 3JS framework. Pure WebGL, we need to get the canvas, and then we need to get its context. 3JS, all we're doing is creating a scene. This scene is sort of the world that we will be rendering. Everything that we add to the scene, that's what we're actually rendering. Pure WebGL, we talked about those shaders, vertex shaders, fragment shaders. Here, we're creating our shaders from another script, and then we're calling that use program. So we're letting our WebGL program know which shaders we want to use. 3JS, we set up a camera. So in our scene, in the world, where is the sort of eye that's viewing everything? We set its position, and we add it to the scene. You can see already it's sort of getting, when you look at the 3JS code, just looking at it makes a bit more sense. When I tell you about fragment shaders, vertex shaders, and all this stuff, if you haven't seen it before, it can be a little overwhelming at times. And if you are going to do pure WebGL, I will tell you right now, you might run away scared once or twice before you finally get into it. That's completely natural. It can be a terrifying thing to get started with, but once you do, it is very rewarding. Here, again, we're setting up our buffers with our position data, and you can see there all those ones and zeros. The joke I like to make is that, if you look at it long enough, then you'll see that it's a square, but I don't know the right person, I don't know any person that would want to write that out for a dinosaur or a world or a tree. That's so many ones and zeros that just, it's mind-boggling. 3JS, well, here's what we're doing. We are creating some geometry, and we're going to create a cube. We're going to give it a material, and we're going to combine those into a mesh. We'll take our geometry, apply the material, and then we add it to the scene, getting the same end result. Step 5, 3JS has no step 5. It doesn't need to work with all those fragment shaders and vertex shaders. But here what we're doing, for our vertex shader, we're saying, take the position of the vertex and use that as our position. So all these points that we've drawn in our world, we're going to just take their position and use it as is. The fragment shader, which actually does the coloring, we're just saying whatever color that point is, that's the color we'll take. We're not doing anything special, but if we start getting into visual effects, if we start getting into more complicated shaders, this section of code will absolutely grow. Step 6, pure WebGL. We're just drawing our triangle strip or our triangles. And in 3JS, one time we have to set up our renderer. We get it from the canvas renderer. We set its size, and we add it to the body. That's one time. Then we call the render function. And we pass it our scene, we pass it our camera, and it does the rest. It figures out based on the materials, based on the light sources, based on the geometry, how it should be drawing things. End result is the same. And sure, this could be presented in many ways. We could put all these lines on all of this code on one line, and hey, it's one-to-one, right? And there's plenty of ways to do it, but the end result is that generally, understanding what 3JS is doing is simpler. And the code to do it will generally be smaller as well.
Shouldn't it be 3.WebGL render? This is basically rendering to canvas. It should be WebGL render.
He's talking about 3.canvas render. It should be 3.WebGL render. Because otherwise you're using the canvas 2D renderer.
This is our 2D render. This is not a
Yeah, he's right.
OK, apologies. It must have had a typo there. So there, when we see 3.canvas render, that should be 3.WebGL render. Yeah, nice catch. So all of that combined, Jonathan will talk a little bit about the very first WebGL project that was put together for the BlackBerry Playbook, which was TunnelTIlt.
Thanks. All right, so we finally had our WebGL implementation in place, and we wanted to make sure that it was functional, that we could actually generate a piece of content for it that would run at a reasonable frame rate. So that's where TunnelTIlt the inception of it kind of came from. We wanted to also leverage various WebWorks APIs as well as HTML5. So we made sure that we added audio and accelerometer information to this game. And we also wanted to package this up as a bar file that eventually you could sell on App World if you wanted to. So the very first game that we came up with actually was not TunnelTIlt, but it was called Slipstream, and it looked drastically different. We were using JSON information, which is very similar to XML, it just has a different syntax. It's really nice with JavaScript, though, because you can take a JSON set of code and you can actually convert that into a JavaScript object really easily. So that's how we were representing our model data. So our normals, our texture coordinates, our indices were all part of this JSON file. And then we were also dynamically loading with XML HTTP requests. I'll talk a little bit more about that combination a little bit later on. But as you can see, this was a very different style, and it was kind of developer-y. We kind of had our developer-y kind of assets. So we decided to try and get some help from the folks in Sweden, our TAT team. So we got some new assets, and TunnelTIlt was born. It had a very different style to it, very non-photorealistic. We had curved tunnels, which gave us some very compelling screenshots. We had this idea that as you're traveling down the tunnel, it's getting brighter and brighter and brighter until you're encompassed in a ball of light. We also were able to achieve a higher frame rate by not being as photorealistic. And overall, it turned out pretty well. So now I'm just going to talk about some of the pieces that made up TunnelTIlt. So I've been talking about JSON information before. So here's a very small JSON fragment over here. And this fragment, we would basically, instead of having a single entry, we would have an array of these entries. But essentially, this is how our levels were built. They were simply just, you'd specify 2 angles, in this case 90 and 270 degrees, and that would generate the wall that you see on the left-hand side. If we specified the angles in the opposite order, so 270, then 90, the wall would actually appear on the other side. And then we also specified a position along our tunnel that our wall would appear. And that's basically all you really need to do to create a level in our game. So in fact, our game is open source, as I'll be mentioning later. And if anyone wants to create any new levels for us, we would love to add them to our game. I think that would be pretty cool. Additionally, I mentioned that we use XML HTTP requests. We were using this to dynamically load new levels. So when the level's done, we would use an XML HTTP request to load level 2, and then level 3, and so forth. So this code, basically all it's doing is, you see this line that says request that open get level.json. Once it's finished retrieving the level file, it's going to call the onReadyState change function with a ready state of 4, in which case we then convert this JSON string into a JavaScript object that we can then use to use as our level. Another thing that's really useful about WebGL is texture loading. For anyone that's used OpenGL before, you need to find your own libraries to load images. So it's somewhat complicated. Fortunately, when you're using WebGL, that you can leverage existing objects. So there's an image class, for example, well, it's not a class, but you can use this image type. And essentially all you have to do is first you create your texture ID on the GPU. You create a new image. You specify an onload function. And then you set the source equal to some file name. And once you set the source to some file name, that image begins to download. And when it's finished downloading, it'll call the onload function. And then once it calls our onload function, we're simply binding to our texture and passing the image data along. So it's actually really nice. It's very, very simplified. OK, so now I'm actually just going to go into a quick demo. If I could have this. How do I close this? There we go. And so this is probably the most stressful part of the presentation, to be good at this thing. But here we go. I've heard it's hard from some people. Here we go. So this is TunnelTIlt. So as you can see, I've got accelerometer data. I'll be able to rotate the device. We've got sound. It's actually got concurrent sound. So if I were to crash, then you would actually hear the explosion sound at the same time. I'm going to see if I can pass this time, though. So as you can see, this looks like any other native application, but this is actually a WebGL application. You can't tell the difference. It's seamless. All right, almost at the end of the level. I just want to show you guys the ending effect. It's kind of cool. So there we go. So I've reached the end of level 1. So I challenge you all to play this game and try out some of the other levels. There's 5 levels in total.
I've never seen that happen before.
Thank you, thank you. Many years of practice, no. So that's basically the demo of TunnelTIlt. I also wanted to talk a little bit about some things we learned by making the game. So this code here looks really scary. So you can download the slides and get a copy of it, or you can take a picture of it. I'm just going to explain more what this does, because it's a pretty useful technique. So, sorry? That code fragment? Maybe I can put it up somewhere. Yeah, I could probably do that. Or at the very least put the slides up somewhere, yeah, that'd be good. OK, so what this technique does is, usually when you're writing an OpenGL program, you have your render loop, and at the bottom of the render loop, you have a GL get errors call, right? And that'll tell you if anything has gone wrong with any of your GL calls. But the problem is, if that gets generated, you still have to find where, out of all the GL function calls that you've had, where that error occurred. And it's a real pain. So what we did with this technique, which was super useful for debugging, is we get our WebGL context, and then we created a debug context. And the debug context, what it did is it took all the attributes from the WebGL context, and then it took the functions from the WebGL context, but it also made sure that after we called each of those functions, then we called GL get errors ourselves. So we actually changed the functionality, which was really cool. It's something you could do with JavaScript. And then we actually put in a debug break. So I don't know, has anyone used Web Inspector here? few show of hands. So we had a debug break statement inside of there. So we'd actually stop immediately when we hit that particular error. So we could isolate it very easily. So it was a pretty useful technique. Another thing that we did, which is pretty common, is so we used triangle strips instead of just using triangles, and we used degenerate triangles. Better, yeah, I said better still. As you can see, the degenerate triangles gave us a bit of a performance improvement, but triangle strips, unless we really made a very dense tunnel, didn't really make that much of a difference for us. But what are degenerate triangles? Probably a lot of you guys are asking, so I'm going to explain. So for starters, triangle strips, like I said, make it so that instead of having 6 vertices of information, we only need 4 vertices of information, right? And then what degenerate triangles let you do is they let you jump from one set of primitives to another location by drawing a 0 area triangle. So that's a useful technique as well. So you can avoid the number of draw calls you need to make. So you only do 1 draw call instead of 1 for every band of our cylinder that we created. So it helps us on performance. And you can kind of see in that diagram what a degenerate triangle, the way you'd specify the vertices. So you do C, D, D, E, E, F to try and create that 0 length triangle, a 0 area triangle. Another thing that we made a mistake. So we accidentally specified a precision for our fragment shader, or sorry, for our sampler, which is what you use for texture mapping. And there was no need to, because it already had enough precision with its default low precision type. And we actually lost a sizable amount of frame rate as a result. We lost like 5 frames per second by incorrectly specifying that precision. So knowing about precision qualifiers is really important. It's also unique to mobile, because in desktop, precision qualifiers are kind of just thrown out. They're not even really looked at. So knowing about what precisions to use for different variables can actually make a difference. In fact, I want to point, so we talked to you guys about learningwebgl.com. Well, here's a particular sample on learningwebgl.com that actually has a bug on our mobile platform. Now, we weren't sure if it was a driver bug at first, but it's not. So let me explain in this particular example. So on Playbook, you're getting that giant white circle, which you don't want, right? We just want a small highlight like on desktop. So what was happening? So the sampler defaults to low precision. And unfortunately, the 255 that we're multiplying by doesn't have a precision associated with it. So on this particular hardware, when we were doing this multiplication, we're actually going to, the texture call times 255 is going to be capped at the low precision maximum value, which is 2. So we're not going to get the result that we're looking for. We're going to get that giant artifact. So there's a couple of ways of fixing this. One, we could increase the precision of our sampler, which we really don't want to do, because that might hurt performance. But instead, what we can do is we can specify a precision for that 255, and a low precision value times the medium precision value will guarantee to generate a medium precision value. So that actually fixes the artifact. But it's interesting because this particular developer was concerned with desktop and not so much with mobile. So it's one of the things you have to kind of think about when you're creating desktop applications, that you also have to consider that these precision qualifiers actually do something on mobile, and you have to be careful about that. Some other performance tips is you can change the quality of your canvas very easily. So you can set a width and height for your canvas, and then you can set a style width and height for your canvas. That'll actually stretch your canvas. So if you stretch it slightly, you might not notice much of a difference, but you'll get a slight performance benefit. Equivalently, if you turn off multi-sampling by passing a second parameter of anti-alias false, that might also give you better performance. I'm going to skip that one. OK, so one other problem that we had with using WebWorks is once we generated our application, you could still scroll the page, and you could still zoom the page, which is a big problem, right? So this is how we got around that issue. So to prevent scrolling, what we did is we had an onTouchMove function, which you can do whatever, if you were going to use an onTouchMove function, you can do whatever you want in there. But at the end, you have to call event.preventDefault, which prevents that event from propagating up to the browser. So your scrolling will no longer work, which is important. Equivalently, we have a meta viewport tag here, which is used to prevent zooming. So you can see that we specify user scalable no. And that'll prevent the zooming operation from working for our game. And then finally, one other thing that we did is we made it so that our orientation was locked to landscape. So if you rotate the device, it won't change the portrait mode. Yes?
If you're doing this in a web app and you're adding it to config XML, how do you actually connect the two?
What do you mean? That's all you have to do. All you have to do is specify and config the XML and
The
I'm not sure how the underlying.
So you're right. So if it's just a web app hosted in a browser, then it doesn't know anything about the config XML, and it won't know to set any sort of landscape or portrait mode.
For Pages or for WebWorks.
No, this does work, because I could show you that it does not actually allow our game to rotate.
In the
pretty
browser.
sure. Because this is a WebWorks application, so it's in the browser, right? So if I rotate it, nothing's going to happen. Also, we also took a look into audio, and at the time, I'm not sure if this is still a bug or not, but concurrent audio with HTML5 was not working for us at the time. So we also had to look into a Flash solution. I'm not going to go into that solution here because it's very long and cumbersome, but you can look at our game online and see how we went down the Flash path if you need to. Hopefully that bug has been fixed by now. I'm not sure. It is? OK, so I've been informed that the HTML5 audio concurrent bug has been fixed. So you can just simply do code like that's listed here in order to do HTML5 audio. Equivalently, we also have the device motion API that we're using, which is another useful HTML5 API, which enables us to get that useful accelerometer rotation data. So I encourage you guys to play the game online. We have it up. It uses a mouse when you're playing in a website. Or you can download the app for free. So far, we've had 73,000 downloads of TunnelTIlt. And we've gotten pretty good feedback, pretty high rating. And the source is also available on GitHub. And if you have any questions about the game at any point in time, you can speak to me afterwards, and you can get contact information. And now I'm going to hand things back to Eric to talk about peaks and valleys.
All right, so I mentioned that when you first start looking at pure WebGL, you might run away scared a couple of times. That definitely happened to me. Peaks and valleys was sort of my first project that I took on that I saw all the way through, and I was really happy with the result. So what it's really intended to be is a learning sample. It combines a number of concepts that you see listed there, so terrain generation, skyboxes, all in one place. The code has been open sourced up on GitHub, so if you want to check it out, I highly recommend that you do so. It's basically one place that you can see how these sort of things are done. And I'll give you a quick look at the application before we move forward. So could I please get the device? OK, so right now we're just looking down at the ground. And you'll see the same sort of controls occurring here. When I touch on the left-hand side of the screen, we have one control for movement. And when I touch on the other side of the screen, we have one control for looking around. And then because we support multi-touch, you can do both of these together. But the things that I want to highlight, just get to the top of the hill here. One is the skybox. You'll notice that no matter where we look, we have a seamless sky pointing down. And there's our sun. With the sun, we have shading. So the close side of the hills here, we have shadows. And then on this side, they're lighter because that's where the light source is coming from. We have the terrain with a bunch of aptly named peaks and valleys. And you can run across this terrain following whatever contours it has set out. Finally, based on the height, you can see that we have different colors. So at the very peaks, we have snow coming down into rock, grass, and then yellow for sand. So can we please switch back? So those were the sort of things that I wanted to encompass all in one application, just as a bit of a starting point and a bit of a proof of concept that can bring all of these things together. So for generating the landscape, there were a number of ways you could do this. There are a lot of algorithms out there, diamond, square, fault. What I relied on there was actually the raised zones algorithm. So diamond square, you start with a grid of points, or you generate 4 points, sorry. Then you use those 4 points to pick a midpoint. Then you draw a diamond, you draw a square, you draw another diamond, you draw another square. In all honesty, I read through the paper on it. It seemed a little complicated. I couldn't get it to go after a couple of days, so I moved on to the fault algorithm. The fault algorithm starts off by drawing one line. And then you draw another line and another. And you do this quite a few times. And each time you draw a line, you raise the points on one side of that line. And eventually, if you do this enough times, and you keep on raising points only on one side of that line each time, you should get something that looks like that. When I was done implementing it, it looked nothing like that. So quickly cancel. Sorry about that. quickly get on back. There were a lot of slides that we went through. All right. Here we go. So fault algorithm relies on drawing lines, raising half of the vertices, and then you get something that looks like that. Mine didn't look like that, so I moved on to just raised zones. So very similarly, we pick some vertices in a certain area, we raise those, and we keep on picking more areas, just randomly generated, repeat a couple of thousand times, average out the heights, and then we get sort of what you saw in the application. The skybox, so when we looked up at the sky, it was a nice smooth sky everywhere we went. Basically how this works is that you put a box around the camera, you paint the inside of it very nicely, and then you make it follow the camera. So wherever the camera is running around in the scene, basically that skybox is following. Now, even though it's right here, the terrain goes on off into the distance. The way you make that happen is by disabling the depth testing when you render the skybox. So you render the skybox first without depth testing, and then you turn it back on. And anything you draw after that point gets drawn on top of that skybox. So regardless of the distance between the camera and the item, it still gets drawn on top of as if it's far away. Basically, it pushes it as far back as possible. Blending on the hills between the various colors, you can also use textures. The way I did it here was all in the shaders. Basically, we start off by defining different colors for sand. There we have a texture for the grass, a color for the rocks, and a color for snow. And we start off with just pure white. That's the first blue highlighted line. Then we call the mix function based on the height of each point. And we mix in however much we need to have of sand at that point. Here, we are saying if the height is within 500 units of the number 400, so from negative 100 to 900, we will blend a certain amount of that color at that point. And based on these breakpoints, we have that blending happening. So something very high up will get a lot more snow and no sand and only a bit of rock and only a bit of grass. Something very low will be all sand and it will have no snow and maybe a bit of grass and a bit of rock. But because the sand is there in so much force, it sort of drowns out the rest of the colors.
What is the meaning of gold?
Sorry?
What is the meaning of VEC4?
So VEC4, that is just a vector. It basically just means I want a number with 4 properties, x, y, z, alpha. So in this case, I'm not using it specifically for red, green, blue colors or anything like that, but here we have between 0 and 1, that defines the amplitude. So at 0, there's zero color, and at 1, there's full color. And here, it goes in the order of red, green, blue, alpha. So here we're combining different colors in different proportions. And that was the end result that we saw there. And big thanks to I can't even say his name, Chandler Prull. That was the first blog that I managed to find information on this sort of mixing occurring. So I always like to say thank you. Traversing, we talked about triangle strips, and we use the same. You can see the animation there with the black line. This is how we define our triangle strip, in this order, moving across. And as we create each point, we get that triangle between the new point and the previous 2 points. And we repeat that to continue all the way. In this case, we have only 25 points, but on peaks and valleys, I believe the number was upwards of 5,000 or so. On each specific point, we have to define exactly how high up we are. And we use the terrain values to do that, but we only have points. We don't know how high up we are in between points unless we do some math. So on the right-hand side there, where that little red X is drawn, you have to figure out how far into that triangle you are. You have to figure out which triangle you're in, and then a bit of calculus tells you, and a bit of trigonometry tells you exactly how high up you should be at that point in time. Physics engines would simplify this for you immensely. But for myself, I wanted to go without any sort of extra frameworks, so I did this myself. And that's it for WebGL, Canvas 2D, HTML5 Gaming. If you do have any questions, we'll hang out here, and there's a round table at 6 o'clock in the main hall. By all means, more than happy to have a discussion. Jonathan as well, if you have any questions about TunnelTIlt or WebGL, he is the main man, and I'll try and pitch in where I can as well. Just want to remind everyone that the 10,000 Reasons to Believe booth is out in the main lobby. If you haven't yet and you want to, by all means drop by and leave us your reason. So, thanks again. Hope you learned something. And again, if you have any questions, just let us know.